so I want to start out with a question, which is kind of like one of the motivating questions for this research, which is how can we simulate quantum systems using quantum computers? Obviously, a lot of this field is kind of birthed out of this question, or like more generally, how do we simulate quantum systems? And I'm using a very overloaded term here, simulate. But what I just mean by simulation is kind of anything that we do with a quantum system on a quantum computer. We'll talk about that a little bit more. So has everyone here seen like the quantum circuit model? Yeah. Okay. So typically, if you know what this circuit is, it's the quantum phase estimation circuit, which is one of the most powerful quantum algorithms. It's the basis of Shor's algorithm and a lot of other cool applications. But the point I really want to make here is that anytime we have a quantum algorithm, we're kind of composing it by a series of operations, right? Series of gates. And the one constraint that we have with all those gates is that they're unitary, right? So U dagger is equal to I. But one question that you might have is that in a lot of your basic physics courses, a lot of the operators that we're talking about are not strictly unitary, right? For example, the Hamiltonian, which governs a lot of the dynamics and properties of these quantum systems, is Hermitian, but it's not necessarily unitary. So that sparks a big question, which is how can we access information about these non-unitary operators in a system that is restricted to only have a series of unitary operations, right? So one way to do it is to use the time evolution operator, right? So if we exponentiate our Hamiltonian multiplied by some scalar number t, we get the time evolution operator of our system. And that is obviously a unitary operator, right? And it encodes the information of our Hamiltonian. And if we assume that our Hamiltonian is written as a linear combination of some operators, then we can use a method called trotterization, construct an approximation to that time evolution unitary. Is anyone having questions on this part? Cool. Yeah, so this is probably like the basic, not the basis, the most commonly used way to access information about non-unitary operators in quantum algorithms, at least for probably the first 20 or 30 years of quantum computation. But another idea of how to access that information is what we call block encoding. And so it's a very general framework for putting information about any operator or any matrix, actually, that's non-unitary inside of some larger unitary. And the way we typically write it is by taking this operator or this Hamiltonian H, and we're going to put it into some unitary, and we're going to stick it in some particular subspace of a larger unitary operator. So now this is a unitary that acts on a larger Hilbert space than just our base matrix, right? In here, we have it in the upper left-hand block of our unitary. That's kind of just convention. But you can imagine that if this unitary acts on more qubits than our system, right? We call those ancillae qubits, so they're additional degrees of freedom. And the upper left-hand block just corresponds to all of those ancillae qubits being in the all zero state. Yeah.
Is it correct to say that in the naive scenario, the size of this matrix is roughly, let's say the number of rows in this matrix is twice as large as the number of rows in the Hamiltonian?
So it would be twice as many if you use one additional ancilla, right? Because each ancilla you introduce doubles the size of your Hilbert space, the number of rows. But it can be much larger.
It could be, okay.
Yeah. So you'll see later, like we'll come up with constructions that use multiple ancilla to block encode. So yeah, these stars are doing a lot of work.
They could be very big, like honestly,
giant.
Much bigger than the original.
Yeah. And that's usually not actually the limiting metric that we care about. But yeah, that's a good question. One other additional thing to note is that the matrix that we block encode is not going to be our normal matrix. It's going to be a rescale version of our normal matrix. And the reason for that is that the magnitude of the eigenvalues of a unitary operator have to be 1, right? So that introduces some constraint on the size of the matrix elements with inside that unitary. So we basically have to scale H such that all the elements of H are less than 1. That's kind of the usual constraint that we use. And we call this lambda the rescaling factor. And typically we want to keep this rescaling factor as low as possible because there's some overhead that we introduce when we rescale those matrix elements. So now, come back to Alan's question. If we see the action of this unitary on an arbitrary quantum state, that's a product between psi, which is going to represent the state of our system, and then a series of m ancillary qubits. So in this case, the dimension of u is going to be something like 2 to the m plus the dimension of psi. Then we see that our output state is going to be h over lambda acting on psi, tensored with the all zero state of our ancillae register, and then just some orthogonal state. We don't know anything else about that state besides that it's purely orthogonal to any state where our block-encoding ancillae are in the 0 state. Does that make sense? Cool. So I really hate this part of the talk, but I'll explain it and then I'll say why I hate it. So in the circuit model, if we picture our block encoding acting on some arbitrary state, right? These top ancillae, these are our block encoding ancillae, the ancillae that we use to generate U. If we apply U onto those series of qubits, and then we measure our block encoding ancilla, then if the block encoding ancilla are in 0, so we measure all these guys and it returns the all 0 measurement, then we know that we're in that particular subspace. And so we output a normalized state of our operator H acting on our system, which is something you might want. And the probability of measuring that all 0 corresponds to the rescaling factor and the norm of that output state. Now, the reason I hate this explanation is because a lot of times people use it to argue that a block encoding is a probabilistic application of your matrix onto your system. And that is true if you view it in this way, but it's a constraint that's not inherent to block encodings. So there's a lot of uses for block encodings where you're not actually trying to probabilistically apply your matrix. But it's a nice way to interpret it in a simple situation.
But I mean, practically, you can separate these things. So you measure, you know you got 0.
Yeah.
Right. And you know you got 1. So then you just separate things out. So then it's just a question of how many shots that you need to do this.
So you could do that for sure. So one example might be maybe I want to apply h squared onto my system, but I only have access to UH, right? I could apply UH. I can measure until I get 0. I could keep discarding my state and then I get 0 and then I apply UH again. And I do the same thing until I get all 0 again. And then I've got h squared on my system, right? But obviously you can imagine that if I keep wanting higher powers of that operator, the probability of success is going to decrease exponentially. But as you can, or I'll get to it in a bit, but there's smarter things you can do than to just keep applying it, measuring. But yeah, that's one application. Another application where you might want to do this, where you measure, is for something like state preparation. So say you have some state that you want to prepare, and you know that state could be written as your operator acting on a vacuum or the all 0. You could use a block encoding to prepare that state. So you initialize all of your qubits in 0, you apply your block encoding, and you measure. And if you get 0, you've prepared the state you wanted. If you don't get 0, you just discard and you start again.
How does this compare to quantum state tomography, like block encoding when a prepared state?
Quantum state tomography?
Yeah. Is it better than quantum state tomography, or is it, I don't know, comparable?
So to me, state tomography means understanding the state that I have.
But you do want to reconstruct the state, right? Essentially, or like if you like, yeah, in that sense.
Oh, that's a good question. That's a good connection that I haven't thought of before. I would use it more as an analog for arbitrary state preparation. So say I have like a state and I can write it with a polynomial number of parameters on computational basis states. That would be very similar to this. And then it would kind of come down to a question of, how many gates do I need to implement UH versus how many gates do I need to do arbitrary state preparation?
Right.
But for state tomography, I think it's a good question, but I think for state tomography, you're more so trying to reconstruct an unknown state.
Right.
Whereas for state preparation using a block encoding, you're trying to prepare a known state. Yeah.
Oh, okay.
Does that make sense?
Right, to clarify my understanding, so when you expand the H into this U space,
Mhm.
are you free to choose the star to
Mm-hmm.
however you want, or are the stars restricted to the fact that you obviously have to be unitary, so? Yeah, I'm a bit, I guess, confused in the,
No, that's a great
Yeah.
question. Yeah, so let's see. So short answer is no, the stars are restricted.
okay,
But a slightly more elaborate answer is that there are technically infinitely many unitaries that
Right.
are block encodings of H, right?
Right.
And so then the question becomes, how do you actually build a circuit that has this form,
Mhm.
right? And that's kind of what we'll get to in the second half
okay,
for our specific case. But you'll see that there are a couple different frameworks for constructing block encodings, and they'll probably all have slightly different values in these stars.
Okay.
Does that answer?
I think it also, this question, to the next question, so you had the, orthogonal state, the red.
Mhm.
So that's orthogonal relative to the side,
It's orthogonal to the psi tensor 0.
okay.
Yeah.
Is that always true? Just from the fact of how U is constructed?
Let's see. Yes, so it would
Okay.
be, if it were untrue, then there would be some amplitude of that state that you could write.
They'll overlap,
That would be, yeah.
okay.
So I'm defining those two states to be orthogonal to each other.
Oh, okay, right, so we're free to, okay.
Yeah.
Thank you.
An easy way to think about it in the way that most block encodings work is that you could think about basically the state of the ancilla
Mhm.
being any computational basis state that's not all zero.
Right,
In which case it'll be orthogonal to the all zero state.
yeah,
So,
makes sense. Thank you.
yeah. Anyone else have questions about definitions of block encodings? Okay, so I'm gonna talk about this a little bit briefly, but this kind of gets back to why I don't like that previous picture of the probabilistic application of block encoding. And that's this concept of qubitization or the quantum walk operator. So this, to my understanding, comes out of a work by Wang Hao and Lei Chuang over at MIT. But say you have a block encoding of matrix H or an operator H. And I'm just going to define H bar to be the rescaled form of H such that lambda times H bar is equal to your original Hamiltonian. Typically, we can find some simple transformation of UH to generate what we'll call WH or the walk operator that has this form. So this is kind of getting to your question about are the stars totally arbitrary? In this case, for the walk operator, they're going to be defined specifically to have this form. And this is written in a two-dimensional subspace. So one column, this column is going to correspond to the all zero state. And then the other state in this two-dimensional subspace is that perpendicular state. And if we define the walk operator in this form, it's going to create basically a rotation about some axis, a rotation around the zero state axis. And is going to look something like an RY rotation. So if you know Pauli RY, it's a very similar rotation gate. It's just in this rotating around a different state. So instead of rotating around the y-axis, we're going to rotate around this guy. And so the reason that this qubitization, oops, okay. So is there any questions on qubitization, rotation? Cool. Okay, so a question that you might ask is, okay, we know what a block encoding is, but what can we actually do with these block encodings? I talked about simulating quantum systems. What does that really mean? Okay, so a question that we often want to solve, or one that I particularly am interested in, is doing eigenvalue estimation. So say I have an operator in some particular eigenstate that I want to target, and I want to know the eigenvalue. You can imagine in quantum chemistry, trying to find the ground state energy or the first excitement state, something like that. We want to find this scalar ki associated with the eigenstate ki. So coming back to quantum phase estimation, right? And actually, who here has seen the quantum phase estimation circuit? Sweet. Okay. So the basic idea is that if I have access to a unitary that implements a function of my Hamiltonian, I can use, or a function of my operator, sorry. I can use this circuit to estimate the eigenphase associated with the eigenstate that I input. So for example, up top, I have u f of h acting on k sub I being an eigenstate of u or an eigenstate of h. It's going to have an eigenvalue e to the I phi I. So I'm going to define phi I as the eigenphase corresponding to that eigenstate. And I can use quantum phase estimation to output a discretized estimate of phi I if I supply the eigenstate on my system register. Does that make sense?
Is UFH here like your block encoding?
Great question. So if I use my walk operator, one of the interesting things is that, I said it was a rotation around some axis. It encodes my Hamiltonian, some function of my Hamiltonian, in this case being a rotation around a scaled form. Then you can see that the eigenphase associated with that walk operator is going to be cosine of or inverse cosine of the rescaled Hamiltonian. And so I can use quantum phase estimation and I'll output some discretized estimate that encodes my eigenvalue k. Does that make sense? So I load up my quantum phase estimation circuit. I supply an eigenstate to my operator, in this case h. So you can think of quantum chemistry. I have a Hamiltonian. I supply the ground state, right? I apply my walk operator a bunch of times. I run the inverse quantum Fourier transform. I measure all of my qubits. That gives me some discretized number. And if I post-process that number, so I just multiply by pi, and I take cosine, and I multiply by the rescaling factor of my Hamiltonian, or sorry, of my block encoding, then I'll output my ground state energy. Does that make sense? Cool. So more broadly, right, this function can be any function, any unitary function. In most cases, it's like the time evolution operator, right? That's one way to encode. It just turns out that the walk operator is one of the simplest functions that we can implement of our operators. But you can imagine some other, complicated unitary function. And if people have more questions on quantum phase estimation, I also have some slides that go into it in a little bit more detail. Okay, so continuing on this train of what can we do with these walk operators, these block encodings. If you apply this walk operator multiple times, you can, if this is my rotation, so this is like the Pauli rotation just written around those different axes. If I apply it multiple times, I just increase the angle that I'm rotating by. Turns out that applying this thing k times gives you the kth order Chebyshev polynomial, if you're familiar with Chebyshevs. One of the really cool things about this is that the Chebyshevs form a nice basis for approximating functions, right? So if I have some random function that I want to implement of my matrix A, I can use my walk operator to construct a really nice basis for approximating that function. And that's exactly what the quantum singular value transformation aims at doing. So in this case, A is my matrix. It's just a generalization of H being a Hamiltonian. But I input A, run QSVT, and I get an approximation to a polynomial function of A. And the circuit looks pretty, this is maybe a very unintuitive diagram of the circuit. But these U's are basically just constructed from W, and these blocks are just controlled phases. So you can think about them as single qubit rotations. If I pick a function that I want to implement, so for example, in solving like ODEs or PDEs, a lot of times people want to solve an equation like AX equals B, right? Where A is a matrix, B is some output state. If you can approximate the function 1 over X, right, then you can solve that linear system. And that's exactly what people do with these Block-Encodings. So, if you want to do fluid dynamics simulations, right, if you can block encode a matrix to encode your fluid dynamic simulations, you could use that to solve the linear system and then approximate what's happening. The tricky part in the quantum singular value transformation is finding these angles, these phis that you need to apply in order to approximate your function. That actually becomes a classically hard problem. It's still polynomial, so it's still efficient, but in practice, it becomes somewhat of a limiting step. But yeah, that's kind of the big picture. That makes sense. So how's everybody doing? No one feel lost? Can I do anything to get you back on track?
I think maybe I was a little confused earlier with your definition of how this has to do with the probabilistic thing. That's totally different. I think the rest of it I'm maybe understanding, but that's maybe a question for later. I don't want to take out the actual topic.
Let's go a little bit further, and then I'm going to come back and we'll see if you.
I have another question regarding that QSBT stuff you're talking about at the end. As a theoretical framework, this makes a lot of sense. Have there been experimental? How challenging is it to get from the theory, even if you have those angles calculated classically, to actually getting something to run in the currently available quantum computers? Have they been very small?
No,
No.
not even close.
So
I would say I feel confident that in the next 10 years, someone will experimentally demonstrate the use of a block encoding or something. But that something is probably going to be the equivalent of running H2 for BQE, right? It's going to be tiny.
yeah.
Yeah, and all this stuff we're talking about fault tolerant quantum computations. We're assuming quantum error correction, logical qubits. Hundreds of logical qubits, and therefore billions of physical qubits. Yeah, for context, I started in NISQ stuff, and then I went to work at Quantum for a while, and now I focus more on fault tolerant quantum computation. So I'm brainwashed. Okay, so we talked a lot about U's and all that kind of stuff, but how do you actually construct the circuits that generate block codes for the parts of that operator? So as far as I'm aware, there are basically 2 frameworks for generating these block encodings. The first is what we call the sparse oracle block encoding or sparse oracle framework. It comes from, to my knowledge, it comes from this paper from Dominic Berry, Andrew Childs. But the idea is the circuit's going to look something like this. So I have my system register psi, I have some ancilla register over some block encoding ancilla, and then I have one additional qubit, which I'm going to call coefficient qubit. And then I have a bunch of Hadamards, and then I have these two oracles. So OA and OC. So OA, we call the value oracle. Its job is to take, if I apply it onto this qubit, which is the coefficient qubit that begins in the 0 state, and then some product state between J and I, where J is a computational basis state corresponding to, I think, the column index, and then I corresponds to the row index of the matrix. Then I'm gonna basically rotate that coefficient qubit such that the amplitude in the 0 state encodes the value of that matrix element Hij. The column oracle is going to take these two numbers, whoops, I switched my notation here, sorry. L should be I. But if I apply my column oracle on a product between J and I, so the column index and the row index, it's going to return the row J, and then the column associated with the ELF non-zero. So you can imagine if I have a sparse matrix, right? I don't want to go over all columns and rows. I only want to go over the ones that I know are non-zero. So the problem, as I'm sure you're all dealing with, framework is that, I was trying to say, like, how do we explicitly construct these circuits? And this doesn't really feel like an explicit construction, right? And to my understanding, that's one of the reasons why these kind of block encoding frameworks died out for a little bit, right? This was back in 2012. And there was not a ton of work on these sparse oracle implementations, right? Typically when someone says oracle, anyone who's not theoretical is going to say, okay, well, if I just have a wizard who tells me things, then I can solve a lot of problems, but I don't have a wizard. And so, like, generating circuits that actually create these two oracles was a tough problem for a long time. And then there's a paper that came out recently, within the past probably 2 or 3 years, that gave a framework for actually constructing these two oracles in a kind of a systematic way. And that's kind of spurred a lot of direction for these sparse oracle approaches. Now, a much more intuitive framework for generating block encodings is called linear combination series. And again, to my knowledge, it comes from primarily Andrew Childs, but Andrew Childs and Nathan Levy. And the reason that it's a little bit more constrained, so assume that I have a Hamiltonian that's written as a linear combination of unitaries, hence the name. You can imagine that these unitaries are, for example, Pauli operators, right? And I have a polynomial number of them, just so that I'm not doing something, exponentially hard. Then I can generate a block encoding of that Hamiltonian using these two oracles. So we call them prepare and select. And although in this slide they might also look a little bit arbitrary, I'll show you exactly how you can explicitly construct that in terms of gates. But the point I want to get across here is that prepare basically just prepares the coefficients of this linear combination, so these alpha L's, and select is going to apply the unitaries associated with those coefficients onto the system, and then I just unprepare my coefficients, and that's going to give me a block of my Hamilton. Now the rescaling factor for this framework is just the one norm of the coefficients of that linear combination. Do you have a question? Okay, cool. So to show you guys how to explicitly construct these circuits, the role of prepare is pretty simple. I apply it onto my 0 state of some ancilla register. The number of ancilla qubits that I need is logarithmic with the number of unitaries I have in my linear combination, right? So if I have 8 unitaries and 3 qubits, and it's going to map that all 0 state onto some superposition over those computational basis states, such that if I square the amplitudes, it's going to give me the coefficients, and they're just going to be normalized by the rescaling factor, so that that state is some real state, some normalized state.
Oh my god. And then like.
Sorry, could you repeat that one more time?
Yeah.
Just like, I'm interested in the target L states. Could you just repeat that one time?
Yeah, so it's going to prepare a superposition over the computational basis states.
Okay.
And the magnitude
Yeah.
or the amplitude of those computational basis states is defined such that if I square the amplitude, I'll get the coefficient associated with that in the linear combination.
I see.
So coming back here, I have a linear combination over alpha L
Okay.
UL, and I want to get square root of alpha L
But-
over lambda.
Before you have like a linear combination of Pauli strings, right?
Mhm.
And here you have a linear combination of computational states.
Yeah,
What is the connection between the Pauli string and the computational state?
I'm so scared.
you'll see in a second.
Okay, good.
Yeah.
Okay,
But
good.
big way. And then the lambda is just to keep the probability of that whole state to be known. Now, if you wanted to write out the matrix of this thing, it's going to look like this. Again, it's a bunch of stars. But the important thing is that we only care about the left column, right? Because we're only using it in a case where we're applying it onto the alternate state of something. And if your coefficients are totally random, right? Then unstructured, you can use Grover-Rudolph, which is an algorithm to compare probability distributions of computational basis states. I can show you what a picture of this looks like. It's just single qubit RZ rotations or RY rotations, and then C naughts. And we know how to do those efficiently. So as long as you give me a polynomial number of these amplitudes, I can generate a circuit that prepares this state or this oracle pretty easily. So let's prepare and if it's structured, so for example, like quantum chemistry or the Fermi-Hubbard model or anything that that the values of those matrix elements are going to be something that's systematic, you can generally construct a circuit that implements prepare much more efficiently than just something like Grover-Rudolph. So that kind of becomes like the art of generating this block code. Now select is going to work in tandem with prepare. So if I supply my ancillae register in a computational basis state L and my system, and I apply select, it's going to apply the Lth unitary onto my system. So you can imagine that if I now have a superposition that I pass in, it's going to apply superposition of those unitaries onto my state. And since they're weighted based on the coefficients, I'm going to get some weighted linear combination of these guys. So select is just going to look a little bit. So this is, again, the brute force implementation of select. I'm going to use this box a lot in the talk, index over L. It basically just means loop over the computational basis states of that register and explicitly control on binary values. So, if I have two qubits and they're both 0, that corresponds to L being 0, and I'm going to apply U0 onto my system. Now I'll go to 1, 2, 3, so on. Does that answer your question now?
Yeah, but so then there's some arbitrariness as to how the terms in the Hamiltonian are ordered. Is that correct? And that really affects like the coefficients that get loaded to each index. Is that correct? So if I were to flip 2 in the way I express the Hamiltonian, then I would have flipped 2 there. At the end of the day, it doesn't matter. Okay.
Yeah,
Okay.
exactly.
Thank you.
Right. Okay. So to formally say this, apply. The role of select is to apply the Lth unitary onto my system when the index is in the computational basis state L, and otherwise it can do whatever it wants. Right. So it doesn't have to just be identity. It can be some complicated function, but the idea is I'm never going to access a basis state that is outside of my range. Right. So I never reach superpositions. And again, just to say, if you have a structured Hamiltonian, right, you can probably find a circuit that's much more efficient than just doing, sequential controls. But if you don't, you can do this. And as long as you only have a polynomial number of unitaries, then the cost of the block encoding is still polynomial. Okay. So now how do I combine block encodings, right? Earlier we talked about if I want to apply h squared, I could apply UH, I could measure, wait till I get a green flag and then apply UH again, wait till I get a green flag. But can we do something a little bit more smarter, I guess? So say I have UA and UB. UA block encodes A, UB block encodes B with their own rescaling factors. If I want to block encode UBA, so B and then A, one way I can construct this is using two ancilla registers and then just taking the product of those two block encodings. It's pretty simple. And the rescaling factor of this block encoding is just the multiplication of the rescaling factors of the two block encodings. So if I want to take a linear combination of these two guys, it's just going to look like this. So I can apply Hadamard's onto some index qubit. I do a controlled application of UA, where this index register is in the 0 state. A controlled application of UB when it's in the 1 state. Apply another Hadamard, and now I get a block encoding of U A plus B. The rescaling factor of this guy is just going to be lambda A plus lambda B. One of the cool things, if wasn't immediately obvious to you, is that this is just linear combination of unitaries, right? To reframe, linear combination of unitaries is this idea just constrained to the idea where these block encodings then are themselves unitary. So A and B are just unitary. So I don't need to create a block encoding since there are unitary themselves.
Does that mean that if you had like a third unitary that you want to add, you immediately need another index qubit because you have to do 0, 1, and 2?
Yeah. But you could also imagine doing something more complicated where I have, some hierarchy of things that I want to. So like A plus B plus C plus D. Cool. Do you have questions over this stuff? Cool. Okay, so now to just go over some useful metrics, talk about how we compare different implementations of block encodings. First is just going to be time complexity. So that's the number of operations. I would say this is the one that I personally care about the most, right? Time to solution. Explicitly, we're going to count the number of non-Clifford operations. For those of you who are not as familiar, we care about non-Cliffords more than we care about Cliffords, because if you're going to assume the surface code as your quantum error correction scheme, which is looking like the direction people are primarily heading, then non-Clifford operations are the ones that are really the rate limiting step in those algorithms. The base of non-Clifford circuits is the T-gate. So we'll count the number of T-gates as the number of steps, number of time steps. And then also arbitrary rotations. And the reason that we do this is we typically implement arbitrary rotations using T-gates. And it depends on how precisely you want to do your arbitrary rotation. But just as a quick back of the envelope sketch, you can think of them about 50 T-gates per rotation. In terms of space complexity, obviously we're going to check out the number of qubits of our circuit. We'll break these up into two components, the block encoding ancilla. So this is the ancilla that I use to generate U, my block encoding of my operator. And then also the maximum qubit usage. And the reason that these are going to be different is that we're going to use what we call clean ancilla in our circuits. And we call them clean ancilla because if they are given to us in the 0 state, we're going to perform our operation, we're going to use them, but we're going to return them in the 0 state. And we're going to promise that any operation we do keeps them in the 0 state as long as they were given in the 0 state. The reason that can be useful is that means that those qubits can be reused throughout the computation for different tasks. So you can think about it in classical computing like you're doing your garbage collection, right? And we're also going to talk about overhead. In this case, I just mean the rescaling factor. As I mentioned before, most of these algorithms roughly scale with lambda. So if I double lambda, I'm roughly going to double the cost of my algorithm. So to do something like QSVT or QPT. Cool. So we have about 15 minutes left. The rest of this is going to be a walkthrough on how you actually block encode ladder operators. But before I get into that, does anyone have any questions they feel they want to get to? All right. So as I said, what are some useful operators to block encode? we just talked about taking products of block encodings and linear combinations of block encodings. So if we can define a basis of operators that we can block encode, then you could imagine constructing block encodings of like more non-trivial operators, right? So if we go to quantum chemistry and quantum field theory, which is where my background is, in quantum chemistry, we can define an electronic structure Hamiltonian, which is just the sum of these fermionic ladder operators. Don't hate me if I'm using B and you're more familiar with A. The reason is that quantum field theorists use A for bosons and B for fermions, which to me is so stupid, but that's what they do. And then also in quantum field theory, particularly if you quote put it on the light front, which is a change in coordinate system from equal time to being on the light cone as you're traveling through time and space. You can write these quantum field theory Hamiltonians in terms of a linear combination of operators that are products of fermionic, bosonic, and anti-fermionic ladder operators. I'm not going to mention anti-fermionic ones just because in our circuits we just treat them as fermionic with some slight modifications that are pretty simple. But so the point I'm trying to make here is that if we can block encode these ladder operators, these fermionic and bosonic ladder operators, that gives us a nice basis for constructing block encodings for Hamiltonians of some interesting systems that we care about. To review the definition of ladder operators, I'm going to try to jump through this pretty quick. But if you apply the fermionic annihilation operator onto your system N, where N is the occupation state, it should, if the occupation is 1, then it should flip it to be 0, and it should apply some parity constraint. So it might, you might get a sign flip. And the creation operator is the reverse. So if it's 0, it's going to flip me to 1. And if it's 1, it's going to 0 out my state or annihilate it, destroy it, whatever word you want to use. This sign, this parity sign that I talked about, is just -1 raised to the sum of the occupation of the preceding modes. I know it's kind of a garbagey sentence, but you can imagine that like every time I see a fermion in any mode prior, I'm just going to flip my sign back and forth. And so whether or not I end positive or negative is just going to correspond to how many fermions were in the system beforehand. Bosonic ladder operators are going to be similar, but we're going to pick up these coefficients that correspond to the occupation state. So if I apply the bosonic lowering operator onto some state omega, I should get square root of omega with the state omega -1. And the creation operator is going to be omega +1. So technically bosonic operators are infinite dimensional, right? Fermions have this nice property that the occupation of a single fermionic mode is only going to be 0 or 1 because of the Pauli exclusion principle. Bosons have no such constraint, so they're theoretically infinite dimensional. So we're just going to impose some cutoff onto the system such that we can discretize it and write it in some finitely sized system. And we're going to call that the cutoff, the bosonic cutoff. So if I want to use some of the prior techniques, the way that people typically block encode these ladder operators is using a linear combination of unitaries. And if I use the Jordan-Wigner transform, or the Jordan-Wigner encoding, I can map each fermionic ladder operator into a sum of 2 Pauli operators. And we talked about if I have a sum of unitary operators, I can block encoding that using linear combination of unitaries. Now, if I have a product of ladder operators, now I get this kind of nasty thing on the right here. And now I have a choice. So I can either block encode each of these fermionic ladder operators individually and then, use the techniques I talked about to construct a block encoding of the product of these guys, or I could fully expand these products out and then block encode that linear combination. In this case, I have 3 sums of 2 Paulis. So if I fully expand that out, I'll get 8 Paulis. But the cost of doing LCU scales roughly with the number of things in your linear combination. So you can imagine that as I keep tacking on fermionic ladder operators here, I'm going to exponentially increase the number of Pauli operators that I have. Does that make sense? Cool. So these are like the known techniques for doing.
Can you go back to the previous slide for a second?
Yeah.
So is there any computational difference between those two forms? Like, is one going to be more expensive than the other?
Yes. And I'll get to that later. But great question. For bosons, we have a similar transform. That's the only one I'll make here. We're going to encode the occupation states in binary. So we use this transform called the standard binary transform to map each bosonic operator into a new combination of Pauli operators. And the number of Paulis that we get out is based on this bosonic cutoff, omega. Okay, so the question that we asked is, can we, instead of transforming into the basis of Pauli operators and then using LCU, is can we find a way to block encode these operators natively and avoid that expansion into the Pauli operator basis? So I mean this to kind of be more of a walkthrough and to kind of build up the intuition for how we construct these circuits. But if we review the rules of block encoding and the rules of our fermionic annihilation operator, we can walk through the action on the computational basis states associated with our system. Right. So if the occupation of our system is 1, and I tensored with the all 0 state on the ancillae register, I apply my block encoding of my annihilation operator, and I want to get out this, potential sign flip, and then my state should be in 0. And if it's in 0, I just want to go to a completely orthogonal state. So this, I'm going to put you guys on the spot for a second. Can you think of a circuit that would do something like this? I'll give you a couple seconds to think about it. Okay, well, the thing that I want to kind of get across is that the action is dictated by the occupation of that state. So I know that if I'm in 1, I want to do something interesting, something non-trivial, right? And if I'm in 0, then I just want to get out of my encoded subspace. I want to just destroy the portion of my quantum state that's in the proper subspace. And so the way I can do this is if Nj is my system, the mode corresponding to this annihilation operator, then I'm going to flip some ancillae qubit from the 0 to the 1 state using a Pauli gate. So that's the operator on the left. The only reason that it's a Pauli gate and not a C0 is just because we're doing a controlled application of our block encoding. You could imagine if I wanted to uncontrollably apply this thing, I just erase that top control qubit. So it's just flip the ancillae if I'm in 0. If I'm in 1, that gate is not going to fire, right? And then I'm just going to do this ZX. In the Z is what implements this potential sign flip, right? So each time the Z gate hits one of these qubits, it'll give me a -1 only if that qubit is in the 1 state. Now, what about the UP dagger block encoding? If you remember, the rules for B dagger are basically flipped. So it should give me PN1 when the state is 0, and it should completely destroy my state if it's already in 1. Don't have ideas. All right. So it's going to look very, very similar, right? I'm basically just changing the condition of whether or not I'm going to flip that ancillae. So, right, as we said for the annihilation operator, I want to push myself into a perpendicular state if my occupation is in 0. For the creation operator, I want to do the opposite. If it's in 1, I want to flip my state outside of my encoded subspace, and otherwise I want to stay in and apply this CX operator. So now, what if we want to take a product of fermionic ladder operators? So if we walk through the action on these computational basis states, right? You can see that when I'm in 0, 0, 1, 0, or 1, 1, I want to flip myself outside of my encoded subspace into some perpendicular state. And if I'm in 0, 1, then I want to apply that ladder operator onto my system. The reason it's 0, 1 is because this B dagger is operating on this left qubit, and BL, the annihilation operator, is acting on the right qubit. So I want my annihilation operator to act on the mode that is occupied, and I want my creation operator to act on the mode that's unoccupied. So the way we can construct this circuit is if the jth mode is unoccupied and the lth mode is occupied, right? That's going to correspond to this 0 and 1. I'm going to use this Pauli gate and a clean ancilla, so an ancilla beginning in the 0 state. And now after this gate is applied, this qubit will only be in the 1 state if it satisfies that computational basis state 0, 1. So I can now flip my ancilla qubit if that qubit is in 0, right? So if that qubit is in 0, it means I'm in one of the other 3 states. The next gate, that repeated Pauli gate, is just to clean that ancilla, so it resets it to 0. And then I just apply ZX on my 2 modes to apply these 2 ladder operators.
So I have a question. A lot of this feels like, I don't know, like a conditional statement when writing code, like check the status of the register. If so, apply this. If not, apply the other. It feels like a conditional if-else statement. But at the same time, as the size of the systems grow, the requirements to do this conditional kind of grow as well.
Yeah.
Do you still get all the benefits that we expect from the circuit simply because you need if the conditions you have to check for grow exponentially, but you're only checking linearly, meaning like the growth of the ancilla qubits is growing linearly with respect to that. Sorry, let me take a step back. Does this scale well as you get bigger and bigger systems?
Yes.
Yes.
And the reason is that the cost scales by the number of conditions, right?
Okay.
You're totally on the right track. I actually want to talk about this more in a CSE way of variables and temporary logical ands is what we call those Pauli gates, because it temporarily stores the logical and of 2 qubits, right? But yeah, it's going to grow with the number of conditions. It's totally independent of the rest of the size of the system. But you can already tell that the number of conditions corresponds to the number of operators that were block encoded. Okay, so what about linear combinations, right? So if I have a linear combination of these 2 fermionic ladder operators, I get these conditions. So it's basically just flip the occupation state and apply this parity rule. So it's pretty simple, right? I don't need any ancilla qubit. I just apply a string of z's and then an X gate on that mode to flip it from 0 to 1. What about a linear combination of products of fermionic operators, right? So these are going to be Hermitian conjugates of each other. So if I go through the computational basis states, right, these are the actions that I want to account for. So if it's in 0, 0, I want to get out negative 1, 1. And if it's in 1, 1, I want to get out 0, 0. And otherwise, I just want to be in some orthogonal state, right? So you can see that kind of the action of this is now dictated by the parity of the occupation of these 2 things, right? If the parity is odd, corresponding to these 2 guys, then I want to flip outside of my encoded subspace. And if it's even, then I want to do my non-trivial update. So if I want to generate the circuit for this, again, I don't, I need 1 ancilla qubit. But now I'm going to store the parity using the qubit itself. So if I do a C0 between the 2 guys, now that qubit, that NL qubit, is going to store the parity of those 2 modes. And if the parity is 1, I'm going to flip my ancilla. And if it's 0, it's going to leave that ancilla untouched. And then I just uncompute, and then I'm going to update my system. And the reason for that, we call this a CZ gate, this guy over here. The reason for that one is just to apply this negative sign onto the 1 state. We can generalize this to like any product of these fermionic ladder operators plus its Hermitian conjugate. And the circuit is just going to look like this. And to come back to your question, Alan, the non-trivial part of the circuit is this computation. That's the only non-Clifford operation happening here. And it just grows linearly with the number of operators.
sorry, to go back to maybe wording a little bit better, the cost of those multi-control gates does not scale exponentially, right? It scales linearly with how many qubits involved, so it's still something you would handle.
Yeah.
Maybe not with today's hardware, but eventually it doesn't scale too bad. So
Yeah.
it's just,
All right, so I'm just gonna show this on, maybe I'll skip ahead to one more thing and I'll run a little bit over time, so sorry. But to compare the efficiency of these constructions versus expanding the Pauli basis, right? If we look at the scaling with the number of active modes, what we call it, the number of unique indices in this product of fermionic operators, this Pauli expansion one in orange, scales exponentially, right, with the locality of the operator, the number of modes. So we actually see an exponential reduction in the number of T gates because our construction only grows linearly. That linear scaling matches this piecewise Pauli, which is doing each ladder operator individually and then joining those block encodings together. But LOBE, which is our framework, is much lower in terms of space. We use only a single block encoding ancillae, whereas the other methods grow linearly with the number of modes. We use fewest number of qubits. And then in terms of rescaling factor, both LOBE and this Pauli expansion method match the L2 norm of this matrix, which is, to my knowledge, it's optimal, but we haven't proven that it's optimal. And then this piecewise Pauli, which is conjoining these block encodings together, has a rescaling factor of 2. To quickly flash what these bosonic operator block encodings are going to look like, we can just use what we call incrementers or adders of classical values to up those occupation numbers. And then we can use controlled rotations to apply the square root of omega that you want in a bosonic operator. If you look at the scaling, ours is better, bosonic cutoff. Trying to be not too much of a salesman here. But you can generalize these things to more complicated products and linear combinations of bosonic operators. You can also do interactions between fermions and bosons. So say you have an operator like this that kind of models a boson being destroyed and a fermion being destroyed or being created together. You can do those guys in tandem. And if you want to benchmark for the Yukawa model, which is a quantum field theory model, if you look at the scaling with the number of modes, which kind of corresponds to the accuracy of that model, or in analog to quantum chemistry, would be like the number of orbitals that you're using to model your electronic structure system. You can see that LOBE is slightly better in terms of all the metrics that we looked at. So just shout out thanks to my collaborators. We've also put out 2 open source code libraries to do this stuff. So Open Particle allows you to manipulate fermionic and bosonic ladder operators together, and LOBE allows you to take those particle operators and block encode them. So you can actually get out circuits in Circ to kind of construct these block encodings. And we explicitly validate them, which is a lot of times these block encoding papers are so big that they can't actually simulate anything. So you'll find that they have a lot of bugs in their circuits. Nice part is that we've tested a lot of it, so we can hopefully trust a little bit that these things actually work. Yeah. So I'm happy to take more questions. I know we're a little bit over time, so I apologize.
we'll do a little clap, if that's okay. We'll have to go, you can leave, if you want to stick around. I'll definitely ask you one other question. What are some of the, like, for the smallest circuits of interest? You mentioned like one of the open source library there. What is like some of the sizes that you're discussing in terms of depth for the smallest circuits, even if you can actually run them in real hardware?
Yeah.
What?
To benchmark, or to validate that, for example, this circuit works, right? The number of qubits that we can officially simulate on our laptop is around 30. If you want to like actually construct the unitary matrix, it's around 20, 25. So you can see that like we only need 3 extra qubits. So you can imagine that the number of ladder operators we can get to is like 20, right? And it's pretty rare that in a physical system you're gonna have like a non-local operator of 20 nodes. Okay? So this is pretty rigorously tested. In terms of the bosonic cutoff, it's a little bit different because you the number of qubits you need depends on this bosonic cutoff, right? So if you allow yourself to have like 100 bosons in a mode, then you need like 10 qubits to represent that single mode. But in terms of these guys, we are not able to even validate this point, but I think it's around like 25 qubits. Kind of grows. You can see, oh yeah, so it's like 30 qubits for that full Hamiltonian. So we're not able to test this one explicitly, but we tested the base components pretty well.
And for a last question, when you're thinking about the measurement for time complexity, kind of saying T gates and everything that's not T gates.
Yeah.
Is there a particular basis that you were targeting for the not T gate part of it? Like, do you divide your circuit up into T gates and any Clifford operation or any specific basis within the Clifford set of operations?
That's a good question. We think mostly in terms of Cliffords, but as you can see in the previous circuits, it's just C naughts and Pauli X, Y, Z, so it's not anything non-trivial about that. So, yeah, you can imagine HST being your base.